Hi, it's Robin. The MOS 6502 CPU debuted in September 1975, which means that little processor that changed the world is now 50 years old. That's a long time, like 96 dog years. So how did the 6502 change the world? Here's my short version of the tale. In 1970, we had no microprocessors. We just had big things. Can you imagine? But in 1971, Intel released the first ever microprocessor, the 4004, for $60. This was a huge breakthrough, but it was just a 4-bit CPU, which is okay for doing calculator-type stuff, but it's a real pain for more general computing where you have more than 16 symbols, like dealing with text. Then in 1972, Intel released the 8-bit 8008 CPU for $120. Now we could deal with 256 symbols at a time, much more useful. In 1974, Intel released the improved 8080 for about $360 for a single unit, and also in 1974, Motorola released their 8-bit CPU, the 6800, for around half the price, $175. Some of the 6800's design team at Motorola identified the need for a lower-cost CPU and started designing it, but were told by management to stop so they wouldn't undercut sales of the then brand-new 6800. So a number of them, headed by Chuck Peddle, left Motorola and joined MOS Technology and continued to design the processor. By mid-1975, they had released the 6501 CPU, which was pin-compatible but not software-compatible with the 6800, and it cost just $20. $20! Predictably, Motorola sued over this, but meanwhile, MOS released the 6502, which had the same instruction set as the 6501, but a different pinout, and an on-chip clock oscillator, and some other improvements. And they sold it for just $25, a small fraction of all their competitors' CPUs. The lawsuit with Motorola was settled with some money paid, and the 6501 withdrawn, but the 6502 survived all that, and then thrived. So the 6502 might not have been the best CPU available, but it was cheap, and it was pretty good, and it could handle pretty much anything required of it. Over the next few years, it was being used to microcomputers and game consoles from Atari, Apple, and Commodore, just to name a few. And by the end of the 1980s, the 6502, including official variations and even unlicensed clones, powered many of the record-breaking systems of the 8-bit era. The first computer to sell 1 million units is the 6502-powered Commodore VIC-20. The most popular second-generation game console, the Atari 2600, or VCS, has a 6507, a further cost-reduced member of the 6502 family. The most popular game console of the third generation, the Nintendo Entertainment System, or Famicom, has an unlicensed 6502 CPU variation. The best-selling Commodore 64 computer, my favorite, has a 6510 CPU, which is a 6502 core with some extra on-chip input-output abilities. All these CPU variations have the same instruction set as the original 6502, and that's what we'll be discussing today. And as an aside, the best-selling console of the 16-bit era, the Super Nintendo or Super Famicom, has a 65-816 CPU, which is essentially a 16-bit 6502. If only they had made a 32-bit 6502, maybe it would have continued to reign. So to celebrate this 50th birthday or 50th anniversary or whatever, it seemed appropriate to make a list of the top 50 6502 instructions. It also seemed a bit stupid, since there are only 56 instructions in total. Anyway, rather than just choose my 50 favorites, I thought I'd arrive at it by some kind of semi-objective method. So I wondered, what's the most executed 6502 software of all time? This would be a good candidate for analysis to make this list out of. I'm talking about a single program, a game, other application software, system software. Could be on ROM or disk or tape, whatever, just as long as it's a bunch of 6502 instructions. Now, you might disagree with this, and if so, make your case in the comments, but here's what I think. There's two front runners for most executed 6502 software ever. One is that best-selling game console, the NES or Famicom. Now, that system has no built-in ROM software at all, not even a tiny BIOS. But as far as I know, every console was sold with a copy of the Super Mario Bros. ROM cartridge. And so that's definitely the most popular game on the most popular 6502 base system, somewhere around 50 or 60 million copies out there. That game got played a lot. Now, I've seen claims that Oregon Trail sold even more, 65 million copies, but there is no way that 65 million is just 6502 based versions of Oregon Trail. If that number is at all true, I'm sure it includes all the later versions of Oregon Trail on MS-DOS and Windows. There were like 5 editions of Oregon Trail for Windows and Mac, mobile versions on iPhone and Android, and console versions, Nintendo Wii, 3DS, Switch, Xbox, PlayStation, etc., etc. Now, I hear some of you say, oh, it was so popular on the Apple II. Listen, there were only about 5 or 6 million Apple IIs ever sold total across all models combined. They did not sell 11 copies of Oregon Trail for every Apple II ever made. No. So the other serious contender besides Super Mario Bros. That I can think of is the best-selling home computer, the Commodore 64. Now, there's been a lot of speculation about the number of C64s sold, with recent credible estimates bringing the number down from 25 million to then 17 million, and lately just to 12.5 million. That makes me a little sad, but I can't argue with science. So maybe the number of Commodore 64s in total is equal to about 1/4 or 1/5 of the number of NES and Famicom sold. However, we're not comparing what's the most popular system here. We're talking about the most executed software. So the Commodore 64, unlike the NES, has built-in software in the form of its kernel operating system and basic language in ROM in the computer. So while Super Mario Bros. Only counts when the NES is powered up with that particular cartridge playing, the C64's ROM code is executing every time a Commodore 64 is powered up. Now, it's true that many games don't use the ROMs, but I'm often surprised when analyzing game code how many do still use the system ROM, at least for scanning the keyboard or loading or some other low-level function. So it still is active. But then there's all the rest of the time whenever you're at the basic prompt, or you're slowly loading from disk or cassette using the stock kernel routines. Even fast loaders still make some use of the kernel routines. Every time someone's typed in a basic program, was using a word processor, was playing a text adventure game, or even most RPGs and so many other things, that C64 ROM code was working away. This might be controversial, but I'm going to say that the typical Commodore 64 was using its built-in ROM code at least 4 or 5 times over its lifetime, more than the typical NES was playing that pack-in Super Mario Bros. Game. You say, but Robin, I played Super Mario Bros. For 100 hours. And I'd respond, oh yeah? I played Ultima 1, 2, 3, 4, 5, Bard's Tale 1, 2, 3, Questron 1 and 2, Wizard's Crown, Fantasy 1, 2, and 3, Hitchhiker's Guide to the Galaxy, Zork 1, 2, and 3, and so many others for 1,000 hours. And you say, but Robin, I meant to say I played Super Mario Brothers on my NES for 1,000 hours. And I say, oh yeah, I programmed my Commodore 64 in assembly language and BASIC and typed in magazine listings for 10,000 hours. Okay, so can I prove that? No. I just wanted a piece of software to base my top 50 list on, and I've now given my reasons for choosing the Commodore 64 ROMs. Take to the comments if you disagree, or if you're so sure it's Super Mario Brothers or something else, go make a video of your top 50 6502 instructions, and I promise I'll watch it. Okay, so now that we've chosen what we're analyzing, here's my method. I took the excellent, ultimate Commodore 64 BASIC and KERNAL ROM disassembly webpage by Michael Style of pagetable.com, and I counted up the uses, the occurrences in the 16 kilobytes of ROM of all 56 6502 instructions. Then I took the top 50 and sorted them in reverse order and came up with this countdown list. So here we go. Coming at number 50, we have TXS. So just to get our bearings on this first one, so for every instruction, I'll be showing the relevant table from Appendix B of the second edition of the MCS 6500 Microcomputer Family Programming Manual from January 1976, released just 4 months after the 6502 debuted. Apparently, Chuck Peddle was on house arrest, so he would sit down and write this thing because he wasn't doing it at the office. If you've read the Basic to Machine Language chapter of the Commodore 64 Programmer's Reference Guide, you'll be familiar with these tables, which seem to be nearly identical, except they were more professionally typeset in the 1982 book. And we'll have a special focus on the 6502 mnemonics, which are these 3-letter names for each instruction that make them easier to remember. And in between them, in the programming manual, they give the official description or explanation for each of the mnemonics. So in this case, TXS is transfer index X to the stack pointer. And I will pedantically offer my own derivation for each mnemonic, which fellow super nerds might find a little more pleasing in some cases, or maybe you'll get angry that I dare offer any corrections to these hallowed historical pages. So the way I remember it is with capital letters on transfer, X, and stack. That's what I'm kind of focused on, is finding the mnemonic, the 3 letters, within that description and capitalizing it. It's important. And for each instruction, I do have some thoughts. So for TXS, of the top 50 6502 instructions as used in the Commodore 64 ROMs, TXS is the least popular. Because how often do you need to play around with the stack? Apparently 7 times, which is the number of times TXS is used in the ROMs. This is one of many, many non-orthogonal instructions in the 6502 set. There's no instruction to move the stack pointer into the Y register or the accumulator for that matter. But that's part of the 6502's charm, I think. And finally, I've selected one example from the ROMs of the use of this instruction. So you get a little taste of the real-world use for it. But don't expect an in-depth tutorial and explanation for them. This video will be plenty long enough already. Okay, so for TXS, at address A683, this routine actually resets the stack and program pointers for BASIC, and that's exactly what this is used for, setting the stack pointer directly. On to number 49, BVS. With 11 uses, the official description is branch on overflow set with capital BVS. Okay, I'll stop pointing out the capitals, but I'll put it on screen for each one there. You decide what you like. Overflow is the name for the V flag. I guess V because O would look too much like a 0. It's like carry when an 8-bit value gets too big and falls over into a 9th bit. And overflow is when a signed 7-bit value gets too big and it kind of spills over into an 8th bit. Now, we won't get in depth there, but for the example here at A59A, it's an example of branching on overflow, which is used by the BASIC token cruncher to skip crunching literal strings and data statements. It's handy for checking that particular 6th bit. On to number 48, NOP or NOP with 11 uses. That's no operation. And I couldn't decide, do I capitalize the OP of operation or the NO of no and then just the P in operation? This instruction does nothing, except it does burn a couple cycles. So it is used sometimes in delay loops, and it's also often used just to patch over unwanted opcodes. If you can't reassemble the code, or for other reasons, you might want code to stay in the same place, and you have to patch it where all the surrounding instructions have to stay in the same location. So you might just patch over it with NOPs. And the example here at E94D, it's actually used to burn extra cycles inside a loop whenever you hold down the control key on the Commodore 64, whenever printing causes the screen to scroll. So if you do a listing or even during a program run, hold down control, and this will execute repeated NOPs in a loop. Will just slow down the process and give you a chance to read it. Next is number 47, BVC, also with 11 uses, branch on overflow clear. So this is the opposite or partner to BVS from number 49. There's several of these branch pairings where you have a branch if a particular flag is set, that is a 1, or in this case, if it's clear, or a 0. And for an example, at AC33 in the BASIC ROM, it's used in this routine to check if the current input is from input, get, or a data read. Again, it's really just like a flag, a bit that's set, and the processor will branch to different code based on the status of that. Next, number 46, PHP, push the processor status on stack, or just push processor status. So the processor status flag holds the results of previous instructions, and they're used to branch based on those results. If you want to know if the last result was equal to 0 or if it's negative, there's a flag for both of those. And sometimes you want to preserve the processor status so you can examine it later. So here you can push it on the stack and then later pull it back and then use it for a branch. So in this example at A871, PHP is used to store the processor status on the stack and then call a subroutine which controls whether kernel messages are on or off, which would otherwise destroy the processor status. And we'll come back to this example because at number 45 we have PLP, pull processor status from stack. It's very important to keep the pushes and pulls on the stack balanced so you don't get a stack overflow. So returning to our example, the processor status is pulled back at A877 and it's used to decide if there was or was not a line number argument. So when you're running a program, whether the program just starts at the beginning or at a particular line number. At number 44, we have CLI with 13 occurrences, clear interrupt disable bit, or clear interrupt disable. This instruction's always kind of bothered me. It's kind of like backwards talk or a double negative. Just hearing clear interrupt almost makes it sound to me like you are disabling interrupts, but actually this is what you call when you want to enable interrupts. So you're clearing the disable bit. It is confusing, but that's how it goes. So this instruction is called by the kernel when you might not expect it, as you'll learn if you have interrupts disabled and you call the character out routine, FFD2, which actually re-enables interrupts. I've had more than a few crashes due to that. And an example of using CLI in the kernel ROM at E385. In this example, it's used to re-enable interrupts after a warm start, like when you hit stop restore. And next at 43 is CLI's partner, SEI, with 18 uses, set interrupt disable status. So I would just say set interrupt disable. There's a fair bit of inconsistency in the official descriptions. Sometimes they'll say it's a bit, sometimes they'll say it's a status. It's almost like they're just making it up in a real hurry to get that CPU released. There's an example in the kernel at E5D6, where SCI is used to disable interrupts while accessing the keyboard buffer. And that's to avoid race conditions, because you don't want the key scan interrupt routine firing while you're playing around with the keyboard buffer trying to take a key out of it, for example. Very useful, just, of course, you got to turn the interrupts on again as soon as you can afterwards. At number 42, we have roll, ROL with 26 uses, rotate 1 bit left, memory or accumulator, or I remember it as rotate left through carry. So roll reminds me that there's no lol opcode. Maybe roll means rotating out loud. Rafflecopter. So for an example, at A982, it's used a few times in this multiply by 10 routine, which converts a basic line number that's stored as text, as PETSCII, as ASCII, and it gets converted into an integer. Roll, or ROL, is essentially a multiply by 2. And if you combine those, you can multiply by 10. At number 41 is roll's partner, ROR, or ROR, with 27 uses, rotate 1 bit right, memory or accumulator, and my version's rotate right through carry. But Robin, you say, you shouldn't include ROR because it wasn't included on the 6502 in 1975. And to that I say, everyone knows it should have been there from the beginning. I call it a bug, whether it wasn't included because it was buggy, or they forgot to implement it until too late, or whatever. Bill Mensch said it wasn't an ROR bug, it was an ROR brain fart by Chuck Peddle. I don't think it was by design. I think it was a mistake, a compromise, and if it makes you feel better to not call that a bug, well, fine. I'm going to call it a bug. Very tellingly, the C64 ROMs use ROR more than ROL, so much for not being useful or necessary or whatever. And for an example, at B93C, here it's being used by BASIC's floating point routines to shift the mantissa as part of the normalization process after a calculation. This code is so much more nasty in a version without ROR. I've seen it. It's horrific. Number 40, LSR. With 40 occurrences, this is shifting right 1 bit, memory or accumulator. I find the official explanation particularly poor on this because L doesn't appear at all. So I remember this as logical shift right. By the way, I'm not taking credit for these other ones. I'm sure I learned them from like Jim Butterfield or somewhere. I haven't tracked down the source for all of them. But logical shift right, LSR. So sometimes you just want to shift something just like ROR, but you don't want that pesky carry entering in through the high bit. You just want a 0 there, and that's what this is for. So for an example, at AE07, LSR is used by the evaluate expression routine to shift the data type, whether it's string or numeric, out into the carry flag. This is pretty frequent. You got a value, you shift it out into carry, and then you branch based on it, or you shift it back in somewhere else. Handy instruction. At number 39, the last of this family of operators, ASL, with 41 uses, shift left 1 bit, memory or accumulator, or I prefer arithmetic shift left. It's actually kind of funny how the official description gets random capital letters while all its shifty neighbors, ROL, ROR, and LSR, do not. Also, my 11-year-old son found it very amusing to pronounce this mnemonic repeatedly. Azl. Anyway, try saying that a few times and see what you think of that. And for an example, here at A3FB, It's used by this routine to multiply the incoming parameter to check if there's enough free space for the required number of 16-bit entries. If you want to multiply by 2, ASL is the instruction for you. Number 38, bit. Test bits in memory with accumulator, or just test bits. So it's interesting that bit isn't really a mnemonic, it's a word, unless all words are mnemonics. So for an example, A598, we first started looking at this crunch routine back at number 49 for BVS. The bit instruction allows that V overflow bit, the 6th bit, to be tested directly. It's a mystifying instruction, but can be very handy. Coming at number 37, CPY. With 43 occurrences, compare memory and index Y, or just compare with Y. So this is the least popular of the compare instructions, which is interesting to me because I would have thought there would be more use for compare Y than compare X. But the 6502 automatically sets the 0 flag when an operation results in a register being set to 0, so you don't actually have to compare X or Y to 0 in a loop. Maybe more Y loops rely on that feature. We'll talk about this a bit more later. But for an example, here in A408, this routine checks if there's enough RAM in BASIC using compare Y to test the high byte of the 16-bit value passed in AMY. Number 36, INX, increment X by 1. Now, this is the least popular of the 3 increment instructions. Further evidence that compare Y isn't used as much because Y loops often terminate in 0. Often X is used as a counter or as an offset while scanning through memory. An example at A38B, here it's used 4 times in a row to skip over 2 16-bit addresses while searching back through the stack for a 4 token, that is a 4 next loop. They all get pushed on the stack, and so BASIC has to scan backwards to make sure there is a 4 next loop there and then look up the parameters and so forth. At number 35, TYA used 50 times, transferring index Y to the accumulator, or just transfer Y to accumulator. This is alphabetically the very last mnemonic in the 6502 instruction set, but I found it amusing that in the second edition of the MOS programming manual, which otherwise sorted alphabetically, they put TYA right after TAY and before TSX, TXA, and TXS. Even though the 6502 instruction section in the C64 Programmer's Reference Guide is based on the same MOS book, they did fix this sorting error in the C64 version. And for an example, here at A3CD, so transfer Y to A only takes 1 byte, and it's used here in this memory copy routine to be able to check if Y is 0 while saving a byte instead of compare Y with 0, which would take 2 bytes. Notice that because Y was changed a few instructions back, the processor status flag would have already lost that 0 flag result from earlier. So this is quite a clever little thing, neat little detail. Number 34, DEX, also with 50 uses, decrement index X by 1, or just decrement X. So this is the least popular of the 3 decrements by a small margin. All these increments and decrements, they just increase or decrease the corresponding X or Y index by 1. As in almost all uses of them, that's what you want to do, is you're using it to scan forward or backwards, or you're using it to count something just 1 by 1. So in that same memory copy routine we were just looking at, X is being decremented after each 256 byte block of RAM is copied, so it is just tracking when it'll be done. At number 33 is TAY, transfer accumulator to index Y. You can transfer between the accumulator to or from X or Y, but you can't transfer directly between X or Y. It has to go through the accumulator. For one more example, in that memory copy routine at A3C6, transfer A to Y is used to hold the low byte of the 16-bit number of bytes to copy, just temporarily in the Y register, since it's free. It's quicker than pushing it to the stack. Even with the 6502 only having AX and Y, you can still sometimes find one free for a temporary storage like this. Number 32, CPX, with 53 occurrences, compare memory and index X, or compare with X. So compare Y had 43 occurrences, and compare X has 53. And I think when we get to some of the other instructions, you'll find that there are more Y uses than X, which is what makes this particular use of X being higher a bit unusual or surprising for me. An example at A403, back in that check stack space routine, the calculated space is compared with the actual stack pointer to decide if there's room for that operation to proceed or if it has to throw an error. Number 31, DEY, decrement index Y by 1, or just decrement Y. And so here we are, of the three decrements, decrement Y is the middle child in popularity. For an example, here at A3EC, back in that block copy routine, Y is decremented after each byte has been copied. So X is being used to track the number of 256 byte blocks, while Y is tracking the bytes within each block. For a lot of algorithms, 2 index registers is enough, and when it isn't, you can just decrement a memory address, particularly in 0 page, to use as additional counters. At number 30, DEC, with 56 uses, decrement memory by 1, and some trivia, this is the first of 3 opcodes whose name happens to not just be a mnemonic for the instruction, but also a hex number. Can you think of the other 2? This matters because when I was compiling the list, if you just do a raw search on DEC, you'll get a bunch of extra hits, which are actually addresses in the left column of the disassembly, which are not actual instructions. And there's one that's over in the parameter area, and that also doesn't count. So that's why when compiling this list, I actually had to go through one by one and make sure every hit was valid. Oh. So for an example, at A3F3, back in that block copy routine, here decrement is used to decrement the high bytes of the source and destination pointers for the block copy. So the Y index is used for the byte by byte 256 byte copy, and the decrement is used to reduce the high byte of that pointer by 1, which is effectively 256 addresses less. Number 29 is EOR with 58 uses, in quotes, exclusive - or, quote, memory with accumulator, or just exclusive or. So it's fun to say Eeyore, but it's not Winnie the Pooh's gloomy donkey friend Eeyore. But did you know that Eeyore, the donkey, actually spells his name EOR, just like this mnemonic? Here in the book, The House at Pooh Corner, Chapter 10, the residents of the 100-acre wood sign a resolution, and there is EOR. By the way, this book goes public domain in just a couple more years. An example of the instruction EOR at A6FC, EOR is often used to toggle bits, such as here in the list routine. Location 0F toggles every time it encounters quote mode, and then that is used to know if the upcoming bytes in the program listing are literals that should just be printed as is and not interpreted as tokens or other characters. Number 28, SEC, with 59 uses, set carry flag, or just set carry. And I just notice again the inconsistency of the language here. In clear carry, it's called a flag, but in the decimal instructions, it's called mode. And in the interrupt disable, it's sometimes called the bit. So it's not always consistent, and they are all packed into the same status register, but that's okay. I only notice these details because I love the 6502. And the flaws, both in the chip and the documentation, only make me love it more. Okay, so for an example at A724, one use of set carry is setting carry before subtraction, which really should always be done unless you know what you're doing, such as here, when basic tokens have 127 subtracted from them to convert them into an index in the keyword table. Number 27, BMI, with 61 uses, that's branch on result minus, or just branch if minus. Now, this is not the body mass index, though did you know that most professional ice hockey players are overweight according to the body mass index? But in this case, the B is for branch and the MI is minus, as in the high bit of a signed 8-bit value being set. But maybe more often it's just a way of branching based on the high bit of a byte, even when numeric positive or negative has nothing to do with it. And for an example, at ABA, well, AABA, almost ABBA, here in the print routine, BMI is used to decide if we're printing a string or a numeric value based on the high bit of 0D, the data type flag. Number 26, ORA, with 62 uses, in quotes, or memory with accumulator. So I kind of prefer to drop the quotes and then capitalize accumulator. This might be the only mnemonic that could legitimately have been just 2 letters, because it's just OR. But to keep the 3-letter standard, they added the A for accumulator, though the similar EOR and don't actually add an A at the end, because that would be breaking the 3-letter rule. And it's kind of fun to say, aura. Kind of has a special aura about it. So for an example, at A5C5, this is the basic token cruncher, and ORA is used to turn the keyword index number into the appropriate token by just setting the high bit. If you take a value and OR it with certain bits set, then those bits in the original number will be forced to 1. It's just used to turn bits on a lot of the time. In this case, the high bit is set because the accumulator already has 80 hex in it, which is binary 10000000. And incidentally, this bit of code right here is why you can type abbreviations in Commodore BASIC, like L-Shift-O. It's adding 128 to the value, and that causes the basic token cruncher to recognize the keyword prematurely, so to speak. Normally, it's the last letter of each keyword that has its high bit set, but you still get a match anyway. I explained that in one of my videos. Number 25, TXA with 68 occurrences, transfer index X to accumulator, or just transfer X to accumulator. Can you believe it? We're halfway through. Yay! You have a value in the X register, but you want it in the accumulator? Well, TXA is the way to do that. Some of these instructions are very simple. So back in the routine that searches the stack for a for next occurrence, if a match isn't found, we transfer the X to A, so then we can add 12 hex, or 18 decimal, which is the size of the for next data structure. You might remember earlier we just did 4 increment X's in a row. That's just 4 bytes. And that was more efficient than transferring to accumulator to add and then transferring it back again. But when you have to add 18, it makes sense to take the extra steps to transfer X to accumulator, do the add, and send it back. 5 bytes versus 12 bytes, for example, of increment X. And yeah, that's because you cannot do a direct add on the X or the Y indexes. You can only increment or decrement them. If you want to add a bigger number, you have to transfer it to the accumulator first. Next, number 24, increment with 69 occurrences. Increment memory by 1, or just increment. Now, how many times I wished INC increment had an implied addressing mode that would just increment the accumulator by 1, just like increment X and Y can do. But nope, that's not what accumulators are for, buddy. You increment your memory or you get out of here. And for an example, at A4E6, here's a different memory copy routine in BASIC that moves memory down when a basic line has been deleted. Increment is used to update the high bytes of the pointers used in the copy after each 256-byte block is copied. Number 23, AND, or AND, with 77 occurrences, in quotes, and memory with accumulator. That isn't really a mnemonic at all, it's just a word, a bitwise AND. I guess that's like bit. I'm going to call it a non-mnemonic, even though it is easy to memorize, but then words are easy to memorize. I already made that point. Okay, for an example, at A459, AND is used to mask out or remove unwanted bits, such as here in the error message handler that uses the high bit to flag the end of an error message's text, but we need to strip it out before the character is printed. It's basically the opposite of or you set the bits to 1 that you want to set in the destination, and you set bits to 1 to allow them to pass through as they are, and you AND with 0 to force it to 0. Number 22, TAX, transfer accumulator to index X. This is the only mnemonic that is a word, but the word has nothing to do with the instruction's meanings. A mnemonic that happens to form the word tax. As we just discussed, and bit are also words, but they actually describe what the instruction does. Unless tax somehow taxes the 6502 in a way I haven't thought of. Maybe. So an example at A54D. So in this routine that relinks a BASIC's program lines one to the next in order, TAX allows X to hold the result of an address calculation temporarily until the rest of the operation is completed. In this case, it's actually less taxing on the CPU. At number 21, we have SBC with 80 uses. Subtract memory from accumulator with borrow. It's interesting, with borrow, is it implying that borrow is the B? I don't think so, and the C isn't justified at all. So my version is subtract with carry, or maybe even subtract. It is interesting. I've been thinking that this is subtract with carry forever. That's how I've had it memorized. But according to the official definition, it's actually subtract with borrow. And weirdly, borrow is defined as not carry, right? Borrow is like the inverse of carry. So calling it SBC is pretty weird, actually. Why not SBB? That seems more correct. Or is the C from within subtract, like I was mentioning? Or is it just to make it seem like ADC, add with carry? I don't know. Or is this a holdover from some of the influences of 6800 or other influences on the mnemonics used? Anyway, an example at A8, A9. This is here in the go-to routine, and the destination line number is subtracted from the current line number to decide if the basic program should be searched from the current point forward to the destination basic line, or if it needs to start again at the beginning of the program. There's actually a small optimization to slightly improve the speed at which a go-to is executed. C64 basic programs are essentially a linked list, and they're only singly linked forwards, not backwards. At number 20, CLC with 88 occurrences, clear carry flag. Okay, so an example at A64E is part of the new routine that erases your current basic program. CLC is used before an add with carry, ADC, to calculate the start of variable storage. That is, it's just 2 bytes past the start of BASIC, and that accounts for the 2-byte null pointer in an empty BASIC program. And clear carry is necessary before most add instructions, unless you know the state of carry already and it's appropriate, because the 6502 doesn't have a carry less add, like it doesn't have an ADD instruction, so it's important to know that it's clear before you do an add. Number 19, BPL with 89 references, branch on result plus, or just branch if plus. But plus essentially means that the high bit of a byte is 0 or clear. So it's a reference to signed 8-bit arithmetic, but that's not the only use here. Many 6500 family I/O chips will put important flags in the high bit because they're easy to test and branch based on their value. The bit instruction also helps in this. In this case, this has nothing to do with plus or minus. It's just whether a particular bit is on or off, such as detecting the source of an interrupt or whatever else. As an example here at AF5F, here in this routine that creates a new basic variable, BPL, branch of plus, is used to branch if the variable is floating point based on the high bit of the data type flag. Otherwise, it's an integer. Plus just means the high bit of the byte is 0, as if it's a signed 8-bit value. But like I was saying, it often doesn't have anything to do with positive or negative. It's just a 0 or 1. It's a bit. It's a flag. Number 18, BCS with 113 references. Branch on carry set. So after subtract or a compare instruction, which is really just a subtract that throws away the result, carry will be set if the values are greater than or equal. So this lets you branch in that case. Some people even have an alias of BGE, greater than or equal to, for BCS. It's also useful if you're rotating bits around and you want to check if a 1 just popped out the end of your rotate or shift. Sometimes subroutines also let the caller know what happened by the state of the carry flag. So BCS and its partner are very handy for this. So an example at EB3A, we're here in the keyboard scan routine in the system interrupt, and BCS is used as a branch if greater than or equal to after checking if the keyboard buffer is full. If so, the key press is just discarded instead of being put into the keyboard buffer. Number 17, ADC, 124 references, add memory to accumulator with carry. ADC is the second of 3 opcodes that happen to be a hex number, in this case valued of a decimal 2780. I had to be careful for these cases when doing the search, and the raw count of ADC was 137, but 12 of the hits were memory addresses in the left column, and 1 was a parameter in the right column, leaving 124 actual references. For an example, at A54B, we're back in the basic relink routine again, and the y-index is incremented as we scan for the null byte terminator at the end of the line. Y has reached the end of the line, and it's then transferred to the accumulator so that ADC, add carry, can be used to add that line length to the beginning of the line, which it's currently anchored on, add the line length, and then you're at the next line of basic. Number 16, PHA, 128 references, push accumulator on stack, or fa. The 6502 just has a single 256-byte stack, which is fixed in memory, so the stack doesn't get used as heavily as it does on other processors where passing parameters to subroutines through the stack is extremely common. Now, it does happen on the 6502, but not so much, and in fact, languages that are really stack heavy have to implement their own software stack to be able to use this freely, like Forth, shout out to Paul Pridham, or C, which are stack-heavy languages. Generally, on the 6502, they need a software stack to handle large amounts of data that get pushed on a stack, especially if you're going to use recursion. Massive amounts can get pushed on there. So as an example, A684, this is that basic stack reset routine. The previous return address on the stack is pulled from the stack, starting at A67E. Then the stack is reset, and then push A pushes that 16-bit return address back on the stack, so control can return to the caller with an RTS, return from subroutine, despite the rest of the stack being wiped out. This is an example of the stack needs to be reset, but we need to preserve the last 2 bytes pushed on the stack so that program control can resume after. At number 15, INY, 134 uses, increment index y by 1 or just increment y. INY is actually the most popular of the three increments, 3 times more common than increment x. And in an upcoming instruction, I'll get into the reasons for that a bit more. So an example at A700, A700 as I like to say, back here in the routine that lists a BASIC program, increment y, INY, is used to step through each character and token of a line of BASIC. The very useful indirect indexing addressing mode only works with the y index, not x. So y is the register of choice for these sorts of scans offset from a base pointer. Very common pattern throughout BASIC and in 6502 in general. At number 14, STX, 137 references, store index X in memory. Here's the least popular of the 3 store instructions. So interesting that it is X that's the least popular when compare Y was the least popular compare. Note that all 3 stores, we're going to be seeing Y and A later, all the stores do not affect the status registers. So that's very useful when you're chaining instructions and you might have some choice in the order. You might be able to make it more efficient by getting your stores over with, and you still have your processor status to branch based on after. So for an example at A9OB, here in this routine that searches for a basic statement terminator, storex is used to store the current terminator being searched for. And what's interesting, it could be either a colon, which the character code for it is 3 AHEX, or it can be a null byte, a 0, terminating the line. So a basic statement can be terminated either with a colon or the end of a line, a null byte. So this is using the clever bit trick to hide one of the execution paths. Hope it's clear that I'm disassembling a slightly different address there. And you see how the code changes based on the code path taken. I really need to do a whole episode on that sometime, but it's a neat 6502 trick. At number 13, PLA. With 146 occurrences, pull accumulator from stack. I was a little surprised to see 18 more PLAs than PHAs in the ROMs. Usually you'd expect them to be balanced, but with so many different code paths, it's not a simple matter of one pull for every push. And for an example of that, at EA81, this is at the end of the kernel system interrupt handler. After it's done dealing with the dataset controls and scanning the keyboard, pull A is used to restore the Y, X, and A registers and then return to whatever it was doing before the interrupt happened. Note that the 6502 isn't able to push or pull the X or Y index registers directly to or from the stack. So this pattern of going through the accumulator is common and necessary. Back to that idea of there being more PLAs than PHAs, it could use more study, but this example I think sheds some light on why. Here's 2 explicit PLAs in a row that are essentially throwing out the return address that's currently on the stack. Now note that return address, those 2 bytes, were placed there by a JSR, a jump to subroutine, not push A's. So that's an example of how the counts would get out of balance like this. And at number 12, BCC, 147 uses, branch on carry clear. And amazingly, is this the only official description that is perfectly written by my pedantic standards? Exactly the right capitalization. Branch on carry clear. Awesome. The weird thing is in my memory, in my imagination, they were all correct like this. And it was only when I worked on this that I realized how many of them did not spell out the mnemonic well at all. This is also the third and final of 3 opcodes that happen to also be hex numbers. And this is the most used. BCC, a raw search, had 159 hits, but 10 were addresses in the left column and 2 were parameter addresses on the right. As an example, at AA22, this routine is called when the parser is expecting only a numeric character. The next character is fetched with the character get routine in 0 page, and it returns with carry clear if the characters from 0 to 9. Then our BCC is used to branch ahead to subtract 2F from the value, even though the value of PETSCII character 0 is 30, just 2F is being subtracted because carry is already clear, very clever, and that converts the character code into a numeric value from 0 to 9 that can then be used in math. If BCC isn't taken, then it branches off and prints an illegal quantity error. Number 11, STY. With 172 occurrences, store index Y in memory. This is the middle of the three stores, and it's kind of interesting that in most ways, the Y index gets more use than X. We've talked about this maybe enough, but it's mostly down to the non-orthogonal design of the 6502 that certain addressing modes only use one index or the other, and at least of the purpose of the C64 ROMs, the Y index ends up getting more use because of indirect index addressing. There's also indexed indirect addressing that does use X, but it's kind of a weird feature. Like, I almost never have a use for it. That's just how it goes. So for example, AB5D, this routine deals with bad input from either the input statement or the read statement. It's interesting, the same thing handles input and read, which is like from a data statement. If it's an input, it's just going to loop around and ask the user to try again to type in a value. But if it's bad data in the data statement, it'll print an error. Here, the high byte of the line number with the bad data statement is in the Y register, and it's stored in 0 page location 3A, so the error routine can report the line number. We're getting to the top 10. Number 10, RTS with 191 references, return from subroutine. No problem with the mnemonic here, except, I'd like the capitalization. But I think you're going to find the official definition of the corresponding JSR very surprising. We'll get to that in a bit. As an example of RTS, just returning from a subroutine at address ACF8. So way down here at the bottom of the data read routine, like most routines, it ends with the RTS instruction, which pulls the return address off the stack and puts them into the program counter so the program can continue whatever it was doing before it called the subroutine. That's all RTS does. Number 9, CMP. With 217 uses, compare memory and accumulator, or just compare. So as an example, at AD80, this is the end of the routine that handles for next loops. Here at 8D80, the compare instruction compares the accumulator with the hex value 2C, which is the PETSCII code for the comma, looking for the optional comma-separated list of variables after the next statement. So C64 BASIC lets you just go next, and it just looks on the stack, but you can also go next A or B or C, which normally just should be the next one on the stack, but you can actually short circuit by specifying another variable that's further up the stack, but you can even specify multiple for next loops in a single next statement. And that's what it's looking for here. Number 8, LDX. With 243 occurrences, load index X with memory, or just load X. So we're getting to the load instructions in the top 8, which of course are all very popular, and load X is the least popular of those 3 load instructions. An example at AE0B. This is in the extremely complicated basic expression evaluator. LDX is used to check if the low byte of the basic text pointer is 0, so it can also decrement the high byte of the pointer before it decrements the low byte of the pointer, and this is while it's backing the pointer up. I don't mean a backup, I mean pointing it lower in memory, backtracking the pointer that's pointing to the basic text, and this is part of recursively evaluating the order of precedence. If you have a complicated line with a bunch of parentheses and pluses and times and ands and all those operators, people hate on Microsoft BASIC, but when I read this code, I am amazed by it. This whole expression evaluator is incredible. Like we're only looking at a tiny bit of it, but I mean, the whole thing, this is some of the most complicated and clever 6502 code ever written, and now it's 48 or 49 years old. I'm amazed. You don't have to be. At number 7, BEQ with 292 uses, branch on result 0, or I think of it as branch if equal EQ to 0. You have to remember the 0 part though. So named because equality is checked by subtracting the values. When you compare, you're actually just subtracting. If you subtract two things and the result is 0, then they must be equal. So that's where this gets it from. But it's always best to say to yourself, branch if equal to 0. That will help a lot of confusion. An example at AF35, we're back here in the routine that handles variables. The two significant characters of the variable name are loaded into 0-page locations 45 and 46x, and then the data type flag is loaded. BEQ is used to branch ahead if the data type is numeric, otherwise it continues on into the string handling. Number 6, JMP with 308 uses. Jump to new location or just jump. So for the alarmists that freak out at the sight of a goto, this is the exact machine language equivalent, and it's the 6th most popular instruction. Your computer is constantly jumping whether you like it or not, and no amount of fretting and doom and gloom about the use of goto will fix that. Sorry. An example at address B013. This routine handles the basic AND operator, which ANDs floating point accumulator 1 and 2 together, and then converts it into a signed 16-bit integer result and puts that in the A and the Y registers. But at the end of the routine, instead of ending with an RTS, as like you might expect, it does a jump to the routine that converts a 16-bit integer back into a float in floating point accumulator 1. And then that routine has the RTS that returns to the caller. So this pattern kind of confused me for a while, but when you think about it, it makes sense. Otherwise, instead of this routine ending with a jump, it would end with a JSR to call the other routine, then that routine would RTS back to here, and then we would have to stick another RTS here to go back to the caller. So it just makes more sense to just jump to the other routine. You save a byte. So this pattern is fairly common, at least in the 6502 BASIC here, but I still do find it a little confusing at times. Number 5, LDY. Load index Y with memory, or just load Y. Of all the load instructions, this is the middle most popular one. An example at B125. This code is at the end of a routine that searches for the existence of a variable name. It does some kind of clever and also a bit of bizarre stuff, pulling and pushing the last byte right back onto the stack. So no change on the stack, but then the value is in the accumulator, and then it checks who the caller was, because that was actually a return address on the stack. It checks who the caller was, but only by the low byte, not a full 16-bit address. It's kind of risky. So it's kind of like there's a 1 in 256 chance that another caller from a different address that shares the same low byte, the low 8 bits of the address, would get confused. Kind of risky. I'm sure they checked for that. So the reason this routine cares who the caller is to decide whether or not this non-existent variable should actually be created. You might know that BASIC automatically creates variables that are referenced if they're being assigned. But if you're just evaluating it, like just printing it, for example, but you've never defined it, then instead of creating the variable, we'll return a pointer to a fake variable, which are just some 0 bytes in ROM. They're actually part of the tables that hold representations of a bunch of powers of 10 that are used to convert floating point numbers to and from a decimal string. But basically, if you don't have variable A defined and you print A, 0 is printed, but variable A is not created. This is hard to explain. It's maybe one of the most hacky, messy bits of code in the entire C64 ROM. And yeah, it's pretty cool too. Like I was greatly amused when I discovered this. I don't think I even knew about this until I was preparing this, and I'm trying to come up with 50 examples. Oh, what was I thinking? Maybe that deserves its own whole video. If you're still listening and you want that, let me know. Maybe I can make it happen. Okay, at number 4, BNE with 386. Hey, that's a CPU. 386 references branch on result not 0, or I prefer branch if not equal to 0. This is the end of all the branches. This is the most popular branch. Equality is checked by subtracting values. If the remainder is not 0, they are clearly not equal. There's an example at address B222, and this is part of the routine that accesses arrays, but first has to scan to see if the array already exists. BNE is used here to branch ahead if it's reached the end of array memory, and that's where it decides if it needs to actually create the array. Number 3, JSR with 730 references, a huge jump up from 386 for the previous one. This is the official description that surprised me the most. JSR is jump to new location, saving return address. All this time I've been saying jump to subroutine. I've been saying it wrong for 40-something years. So my abbreviation is either jump to subroutine. I still prefer that, it's shorter. But you can get the mnemonic out of the official one with capital J, jump to new location, S for saving, and capital R, return. Jump, saving, return. JSR. Did anybody else think of JSR as saving, return? Okay, an example at B316. Later on in the array access routine, JSR is used to call a multiply routine at B34C to calculate the address of array data. Did you know that 6502 Microsoft BASIC can handle up to 7-dimension arrays? Like A bracket 1, 2, 3, 4, 5, 6, 7? That is like syntactically legal. Of course, you run out of RAM extremely quickly when you start multiplying 7 dimensions together. That routine is certainly very taxing on the CPU. There are no multiply or divide instructions on the 6502 CPU. And we're at the number 2 mnemonic, STA, with 745 occurrences. Store accumulator in memory, or just store accumulator. With just one accumulator, if you want to store your results, this is the way to do it. I guess it's little surprise that this is the second most popular instruction. As an example, at B404, this routine evaluates functions, and as part of the process, a pointer to the function, this is basic functions, DEF, FN is how you define one, and then just call it with FN and the variable name. A 16-bit pointer to the function is stored in 4E, 4F hex, and it's pushed on the stack and evaluated, and then restored. So I could do more study on this, but I think this is done because functions can be nested inside each other and evaluated recursively, but I haven't totally figured this out. Just seemed like a very interesting use of store A in context. So this is something to investigate more thoroughly, or if you already understand how this works, please explain. But again, this is just one or two of the 745 uses of STA, the second most popular instruction. And now the moment we've all been waiting for? No! Because I couldn't resist, I am going to do some honorable mentions here. Honorable mention number 1 is TSX with a total of 6 uses. This transfers the stack pointer index X. While I was preparing this, my aforementioned 11-year-old son saw TSX and was looking at the sheets with me. He said, "Why isn't there TSY?" And I answered, because the 6502 instruction set is non-orthogonal. And he replied, "Oh." So an example at address FF4D, we saw the end of the main system interrupt handler earlier, And here's the beginning of it, where the A, X, and Y registers are pushed on the stack. But then TSX is used to get the stack pointer into the X register, so the status register, which is automatically pushed on the stack when an interrupt happens, can be examined. Note that while the stack starts at address hex 0100, we're offsetting from 0104 4 bytes to reflect the fact that 3 bytes were pushed on the stack just now, and we want to reach back to the processor status that was pushed on before. Then we're checking the processor status to see if the BRK flag is set, and then branching to either the break handler or the regular IRQ handler. And next, honorable mention number 2, RTI, return from interrupt. So there's only 2 RTIs in the whole C64 ROM. We already saw the one of them in my entry for PLA at the end of the IRQ handler. Here's the other one for the NMI handler, which happens during RS-232 communication and when you hit the restore key without holding down the stop key. And finally, honorable mention number 3 is CLD, clear decimal mode. While this was easy to choose the example since there's only one use in all the ROMs, it's used here in the system reset routine. Whenever the system boots or is reset, the flag is cleared, as I don't think the 6502 is guaranteed to come up with decimal mode clear after power up or after it's reset. It's a good practice anyway. So if decimal mode is enabled, the ADC, SBC, add and subtract instructions behave differently, adjusting the results so they're valid binary coded decimal every time. But I think there should be at least 1 or maybe 2 more uses of CLD clear decimal mode in the ROMs, and that's at the beginning of the IRQ for sure, and probably the NMI handler. I need to study this more, but subtract is used in the kernel Jiffy clock every interrupt to check for the 24-hour rollover, and it does it by subtracting a 24-bit value. If the interrupt occurs while you have decimal mode enabled, almost certainly that calculation goes wrong. So I don't know if anybody's ever done a full analysis of that, but I do think that's a bug. You know, I guess one that will be fairly easy to fix if you can squeeze an extra CLD in. Okay, and number 1, no. Sorry about this, but you know what? Now that I've gotten to 52 of the 56 instructions, I gotta mention them all. Let's call this dishonorable mention number 3. It's SED, set decimal mode, the opposite or the partner of clear decimal mode. And for an example, there is no example. After so many hours of preparing for this, it was both a relief and kind of funny to find the 3 instructions that weren't used at all. So there's no example, but set decimal mode definitely has its use if you're doing BCD, that is binary coded decimal math. It's certainly not a useless instruction, but there's no use for it here in the C64 kernel or BASIC, which don't use binary code decimal at all. The reason it was included in the 6502, people might want to make cache registers or calculators with the 6502, and it's handy there. Dishonorable mention 2 is BRK. Again, 0 occurrences, force break. So the BRK instruction, break instruction, isn't used at all in the kernel either. Its opcode happens to be 00, and that byte pattern, of course, does occur in the ROMs, but I don't believe any of them are ever intended to be executed. That is, they're data or maybe uninitialized bytes. Now, this is also not the most useless instruction, as it can be used as a software interrupt, as a breakpoint to send control to a machine language monitor, such as Jim Butterfield's Supermon, for example, which can be super useful for on-machine debugging. So it's a neat instruction, and I guess it could use its own video sometime too, but you can write a lot of programs and never use it. And finally, dishonorable mention number 1, CLV. Again, no occurrences, clear overflow flag. So here is the most deserving entry in the dishonorable mention, demonstrably the most useless 6502 instruction of them all. If I've ever used it, I don't remember it all. I can't even think of a good use for it, really. I guess if you're going to do some signed 8-bit addition, you might want to call it first, I guess. I don't know. You could even simulate it with push something on the processor stats and then pull. You could set or clear it if you want. So it's really not necessary. Now notice there is not a SEV, set overflow instruction at all. So this is the only one that doesn't have a partner. Just kind of further indicating how useless it really is. You know what? If they had left clear overflow, CLV, out of the instruction set in 1975 instead of ROR, they probably wouldn't have got a single complaint ever, and it would still be missing 50 years later, and no one would care. Poor CLV. Except, wait, that's not the final word on CLV. My patron's early access to this video, and upon viewing it, channel friend and occasional collaborator David Yaud told me there is a fairly frequent use for CLV. Not in the Commodore 64, and in fact not on any of the other 8-bit system ROMs I had checked, not the VIC-20, the Apple II Plus, the Atari 800, even the Oric doesn't use CLV in system ROM. So where is it used? Well, it's been patiently sitting there for years right beside the C64. Commodore's floppy drives, such as the famous or infamous 1541 disk drive. Ignorant me, I had no idea. So here's a bonus section newly made to help cure my CLV ignorance, and maybe some of you need this too. So I've been using the Super Snapshot Machine Language Monitor to examine the C64 ROMs throughout this video, but it also has a feature to examine the memory of some peripheral devices. Just type *8 to indicate device 8, and now the memory inspect routines will be directed to the disk drive. There are in fact 30 occurrences of CLV in the 1541 ROM, enough that would have ranked around number 41 in this C64 list if we, for some reason, cherry-picked that one thing. But almost all of the uses of CLV follow a surprising pattern. So if I disassemble at FCB8, you see here there's 3 CLVs. But immediately above each of them is a BVC, branch on overflow clear, and they're branching right back to themselves. If overflow is clear, then this is seemingly a very fast but infinite loop, just 3 cycles every time the branch is taken back to the beginning of the instruction over and over and over. Normally you wouldn't do this. You would branch back at least one more instruction and check if an input-output register has changed or something like that. How can the overflow flag get set when the CPU is stuck in this infinite loop? Well, if we look at the 6502's pins here in this diagram, up near the top right is pin 38 labeled SO. The brief write-up says that's the set overflow flag. Set overflow. So instead of a set overflow instruction, the 6502 has a set overflow input pin. Now, it didn't get much use in most computers, it seems, but on the 1541 and other Commodore disk drives, they use this SO pin to signal when the drive has finished reading or writing a full byte of data. So this tight loop exits as soon as overflow is set, but then it needs to clear it. And the pin can't do that. The pin sets, and then the CLV instruction here clears it. So that's why this pattern is repeated something like 27 times in the 1541 ROM. It's waiting for a full byte to be read or written before continuing. What teamwork! Note that the 6510 does not have this SO pin. I'm sure it was dropped in part to make way for the 6 input-output pins labeled P0 through P5 down on the bottom right, since the 6510 was still being squeezed into a 40-pin dip like the 6502 was housed in. But as I was saying, even most systems that have a 6502 with the SOO pin still don't use it, it seems. Thanks to David Youd for bringing this to my attention, and while I'm at it, check out his book, EOR FF 6502 Ponderables and Befuddlements, which actually has a small section about CLV starting on page 67. There's a free PDF of his book on archive.org that you can download, so please check it out. Link in the video description along with many other useful resources. And on that note, finally, I can delay no longer. The number 16502 opcode from the 50-year history of this world-changing processor. Number 1 is LDA. Official description, load accumulator with memory. Load accumulator. So finally, load A. Was there any doubt? Towering above the competition with its 1087 references, it gets more use in the C64 kernel and BASIC ROM than the lowest 33 opcodes combined. I mean, you'd be hard-pressed to do without those other opcodes, except for, well, the 3 that weren't used at all, so 30 of them. But still, just kind of shows how important load A is. That's what happens when you only have one accumulator, one general purpose register. And our final example today is at address B518. How was I to select one example out of so many? How about here in the routine that checks for free space to allocate a string? So at B518, the garbage collected flag is loaded, and if even after the dynamic garbage collection, the string garbage collection is done, if there's insufficient room for the new string, the high bit of this flag is set, resulting in an out of string space error being printed, and the program ends. And likewise, I think we can now print an out of 6502 instructions error, and conclude this top 50 plus 6 list. One thing I learned while preparing this is that many of the mnemonics come from the 6800 CPU, as you might expect, given the history I explained earlier, but I was surprised to learn that many of these mnemonics actually originated on the PDP-11. So they weren't original to the 6800, and the 6502 no more ripped off the 6800, it's to the PDP-11 that these mnemonics are due. And so I hope this is a complete list. The shared instruction names between the PDP-11 and the 6502 are here in alphabetical order. I'll put on screen, I don't need to read them all. Those are all the instructions that are shared between the PDP-11 and 6502. I should clarify, the names of the instructions are shared. The PDP-11 has a very different architecture that I can't claim to really understand, but I know that quite a few of these instructions behave differently. It's not really the same instruction set. It's the same mnemonic names. But anyway, it seems very clear that the designers of the 6800 and 6502 took some inspiration from the PDP-11 in this way. Thanks to my patrons, especially for this particular video, thanks to my very generous patron, Michael Style of pagetable.com. His website is full of great articles and resources that he makes freely available. That's why I'm saying he's generous, and that he's a patron. And in particular, the ultimate Commodore 64 BASIC and KERNAL ROM disassembly has been a fantastic resource while working on this video and many other past videos I've made. So definitely check out the link in the video description, and thank Michael for all his hard work. Thanks to you for watching, and we'll talk to you next time.
The 6502's the CPU for me, produced by MOS Technology. Pedal made it with his team. Those 8-bit registers are a dream. It first powered the Apple I. Few realized what had begun. A low-cost processor a solution, sparked the home computer revolution. 6502, a technological breakthrough. 6502, a technological breakthrough. Soon came the Commodore PET. Model 2001 had a built-in cassette. Then there was the Atari 2600, originally known as the VCS. VIC-20 and the BBC Micro, great computers, although they don't compare with what I adore, my favorite computer, the Commodore 64. 6502, 8-bit through and through. 6502, 8-bit through and through. So many great machines use that chip, an inexpensive 40-pin dip. From humble origins in monochrome to a computer in nearly every home. 6502, a technological